high pressure physics has been a pretty broad and mature field. It's been in existence for probably about 40 years or maybe even more than that. People like to do, geologists particularly like to do work under high pressure because they want to know how materials behave when they are subjected to pressures that are close to that of the interior of planets. Material scientists like doing work on high pressure because it allows you to sort of go into a different phase space. Something happened. Hello? Okay. Working again. Maybe I just turned it off by accident. That's possible. Material scientists do work under pressure because by doing work under pressure, it allows them to look at how materials behave when the atoms are squeezed close to each other. It allows them to simulate new kinds of materials. It also allows them to learn about the properties of materials under the situations where the atoms are squeezed together, so that they might in fact discover a new property that might not exist in the material when it is at zero pressure. So this is sort of the general kind of motivation for why people do work under high pressure at all. Now, so what I'm going to do today is to talk a little bit about pressure itself, how one produces pressure, and then I'll talk a little bit about semiconductors and quantum bells of semiconductors. I'll give you a little bit of a background on these materials and then describe for you an experiment that we did many years ago under pressure. And then finally, at the very end of the talk, I will spend just a few minutes giving you a glimpse of how high pressure has affected various discoveries in superconductors. From what I hear, you're all a very mixed audience. There are folks over here who are specialists in high pressure, P.G. Ramesh, for example. And then there are folks who are probably not scientists at all. So some of you will probably find that you know everything about what I'm saying, and hopefully for the others at the end of the talk you will too. Okay, so let's talk about pressure itself. I'll talk about the units, ranges of pressure, and how you produce pressure. So, when you apply pressure, you think about squeezing stuff. So for example, if I take this object, imagine that this is a crystal, and I push on it, I squeeze down on it, and hopefully not turn it off. I squeeze down on it, I push on it on one direction, and when that happens, the object, let's try that again. Okay, there we go. The crystal gets squished so that it becomes shorter along the vertical direction, and of course it kind of probably pushes itself out a little bit along the horizontal. So the atoms come closer together, but then the shape of the object is also distorted. This kind of pressure is called uniaxial pressure because you're applying pressure only along one axis. The other kind of method that one uses to apply pressure is when you apply pressure from all directions. So you take this object and try to apply pressure from all different directions. And in order to do so, what one needs to do is to, physically it would be hard to do, but the easier way to do it is to put it in a bath of some kind of hydraulic fluid, sort of like the brake fluid in your car or your scooter, and then push down on that hydraulic fluid so that the pressure is transmitted equally along all different directions. And what that does is it pushes all the atoms closer together, makes the object smaller, if you like, but it keeps the shape of the object. So the crystal in the uniaxial situation, the crystal's symmetry, if you like, was changed because it was no longer a cube. But when you apply hydrostatic pressure, it still has the same shape. It's still a cube, it's just that the atoms are closer together. Now, the processes of applying pressure are somewhat different. The big difference while we are making studies is that if you apply uniaxial pressures, and it turns out you can only apply a fairly small amount of pressure before the object just snaps or breaks. So for example, just in units of gigapascals, for silicon you might be able to apply 2 gigapascals of uniaxial pressure before it breaks. But if one applies hydrostatic pressure, then the atoms kind of have nowhere to go. And so they're all still stuck together, and you can apply very much larger pressures. You can apply 200 to 300 gigapascals rather than just 2 gigapascals. So of course one can look at very different ranges of the atoms being squeezed together. Alright, so now let's talk a little bit about the units. I said the word gigapascals without telling you too much about it. Pressure is just force over area. That's what we learned maybe in 7th grade or something like that. In the metric system, the unit of pressure is a Pascal. And a Pascal is equal to Newton per meter squared. And a Newton, it could be any kind of force, but if one thinks about how much a Newton is, the easiest kind of force we can think of is the gravitational force. And if you want to produce 1 Newton of gravitational force, force being equal to mass times g, right, the acceleration due to gravity or the strength of the gravitational field, to get 1 Newton of pressure, you would have to take an object whose mass is 102 kilograms or 102 grams, and then of course when you multiply by that 9.8, you end up getting a force of 1 Newton. So if you want to produce 1 Pascal of pressure, what one needs to do is to take an object that has a mass of 102 grams and a square area of 1 meter squared, and then you lay it on the ground or wherever. I just happen to have such an object. There you go. Some piece of fabric that quite fortuitously has a mass of 102 grams and a square area of just about 1 meter squared. So if I take this and I lay it on the ground, that piece of fabric now applies a pressure of 1 Pascal on the floor. Okay? Now, in order to squeeze atoms close to each other and see any kind of interesting effects, one has to apply very much larger pressures. The kind of pressures one would like to apply is something of the order of gigapascals or 1 billion pascals. So imagine 1 billion such pieces of cloth stacked one on top of each other, and that would be 1 gigapascal of pressure. So it's in that range of pressure that we'll be operating in order to make our studies. Okay, so what are the ranges of pressure in the universe? It turns out that pressure has one of those very large ranges throughout our natural universe. Out in interstellar space, the pressure is about 10 to the negative 15th pascals. And that's where we have, one atom or molecule per several square miles, cubic miles probably. In near Earth outer space, the pressure is about 10 to the negative 4th of a Pascal. So this is kind of looking at the vacuum ranges. The Earth's atmosphere applies a pressure of 10 to the 5th pascals, 100,000. And then, as we go further higher, the core of the Earth has a pressure of about 10 to the 11th pascal. A 60-kilogram person in high heels applies a pressure of about 10 to the 7th pascals. And then up by inside the core of the Sun, the pressure is of the order of about 10 to the 17th pascals. So this is the very enormous range of pressure that one sees in the natural universe. And so, of course, if one wants to study what's happening in the interior of planets and so on, one has to get into the appropriate range, such as that in the core of the Earth, in order to apply that much pressure to see what's going on to those materials. So today I'm going to be talking about this range of pressure, from approximately the Earth's atmosphere to about the core of the Earth. That's approximately the range that most people have managed to achieve so far through the method that I described. So that's about 300 to 500 gigapascals. Most of our studies in our lab are at somewhat lower ranges, going to about 7 or 8 gigapascals. But for several of the other kinds of experiments, it is possible to go much higher. Okay, so now let's look at the kinds of stuff that happen when you do apply pressure. I showed you a few of the ranges, but let's see what happens to kind of some ordinary kind of material, such as water. If one applies pressure to water, hydrostatic pressure, it turns out that when you apply approximately 1 gigapascal of pressure, water turns into ice at room temperature. So the changes are pretty drastic. The crystalline, the geometric nature changes, the molecular interactions change, and so on. And so one can see all kinds of interesting things that you would never see at atmospheric pressure. So fundamentally then, what hydrostatic pressure does is it squeezes the atoms of the substance closer together. That usually increases the intermolecular interactions in the material without changing the chemical composition of the material. And as a result, the electronic, vibrational, optical properties of the materials change. For example, if one takes a material like gallium arsenide, it's a very common semiconductor. Gallium arsenide has this ugly gray color at atmospheric pressure. When one applies about 5 to 6 gigapascals to this crystal, it turns bright red. So some of them are actually visual changes as well. And then, of course, there are changes in the molecular crystalline geometry, as we saw for water. And this kind of studies then allows scientists to simulate new kinds of materials. Okay, so let's talk now about how one produces pressure. How does one produce these high pressures? Well, as the name implies already, one uses the diamond anvil pressure cell. And I thought I would spend a little bit of time telling you about how the diamond anvil pressure cell works, and how it's all put together, so that you get a sense for how the actual equipment looks like. One would think that to produce such high pressures, you need some gigantic piece of equipment, lots of gears and trunking wheels, and maybe pumps and a whole bunch of noise, and big signs out there saying, "Stay far away, we're producing high pressure." But in fact, the diamond anvil pressure cell looks something like this. Actually, it looks something like that. Okay, that's the diamond anvil pressure cell in this equipment. It's pretty small. It's much smaller, as you can see, than the hand of this person. How does that work? I mean, how is it that we can use such a small piece of equipment in order to produce such high pressures? Well, the trick to doing that, really, there's several tricks to it, but one of the fundamental trick is to remember that since pressure is force over area, if you want to produce a very large pressure, you can apply a big force, and that will allow you to produce a large pressure. Or, what you can do is to use a very small area. Okay? To get the same amount of pressure, you can just decrease the area a lot, and then therefore apply the high pressure. So in other words, if I go back to my little demonstration over here, right now I have 1 pascal of pressure that this piece of fabric is applying on this ground. And what I can do is to decrease the pressure. It's hard to fold it with just one operating hand. Okay, there we go. 4 times less area. So if I put this on the ground now, I'm going to get 4 times as much pressure, right? And of course I can continue doing this. Fold it, decrease the area. My force is not going to change because the mass of this object hasn't changed, and therefore the gravitational force hasn't changed. So by just making the area smaller and smaller, I can just increase the pressure that is applied. So this is the idea of using the diamond anvil pressure cell. Why diamonds? It's because diamonds are some of the hardest materials known to mankind. And even though our forces are going to be moderate, you still don't want something that's going to shatter on you. So diamonds turn out to be a really good material to use as you apply those forces. And so, diamonds, well, it's kind of hard to get a gigantic diamond like that, right? So we are kind of limited as to the sizes that we can use. Most of the precious metals use diamonds somewhere around a 1/3 carat size, or maybe a 1/2 carat if the group happens to be rich enough to buy a 1/2 carat diamond. So you have to use a fairly small diamond, but then now you've got to really go down and decrease the area over which the pressure is being applied. Okay, so how does that work? Here's a diamond. This is a standard brilliant cut round diamond that people see in engagement rings and in earrings and stuff. It's the same kind of brilliant cut that one uses. And then what's done is, in order to apply the pressure, we can't really use this little point over here because that would be too small an area. So instead, what one does is have diamond manufacturers cut off the tip to produce a rather small culet over here of about 1/2 millimeter or so in diameter. And then one has to now set this up inside some kind of a device so that you can hold the diamonds stable as you push them towards each other. So what one does is one sets it up in a seat, one epoxies the diamonds into the seat, and then that's what it looks like. And it looks pretty ugly by the time we're done with all that black epoxy. And then you need 2 of these diamonds so that you can push them against each other. So this is then the fundamental opposed diamond setup for a high pressure cell. Now, the high pressure cell happens to be a kind of a slightly unforgiving device. I tell my graduate students that they're not allowed to drink coffee the day they're going to come and work my diamond angle cells. So that when they're doing all the alignment, you really have to make sure that things are done very precisely. But at the same time, you don't want them to bump one diamond up against the other and break the diamonds. So what one needs to do in aligning the diamond angle cell is to make sure that as the diamonds are close to each other, that their tips, their edges, are exactly aligned one on top of the other and not shifted as it is shown in this image. The second thing one needs to worry about is that we should have these diamonds exactly parallel to one another and not wedged as is shown over here at an angle. Now that part of the alignment process actually uses a very simple kind of experiment that most BSc students do. That is one of looking at interference fringes in a wedge configuration. And we use exactly that same method in the lab to make sure that the diamonds are parallel with respect to each other. So what one does is one has a beam of light coming through the bottom. You look at it from the top. And as you look through the diamond angle itself, one looks at the culet, and you can see interference fringes. These black and white fringes show you that there is a difference in the thickness of the air pocket between one edge of the diamond and the other, so that they are somewhat wedged with respect to each other. Now the diamond faces themselves are polished very, very flat to about 1/10 of a wavelength of light, and so therefore you can see these interference fringes very well. And as one gets these 2 diamonds into more and more of a parallel configuration, you come to the point where you start to see just one fringe of all the different colors kind of spreading apart. And at the moment where those colors vanish and we just get a white field, we know that our diamond angle cell is perfectly aligned. The 2 tips, the culets, are parallel to each other, and they're also exactly lined up along the diameter. Okay, so our diamond angle cell is sort of ready to go. We've gotten it all aligned, and now we are ready to put the material in between the diamonds in order to apply the pressure. So then how do we do that? Well, if we have just a diamond angle cell like that, we just stick a piece of crystal in between the 2 diamonds, then all we have is a bunch of crushed crystal. So remember that whole thing about hydrostatic pressure. We need to have a fluid in there, to transmit the pressure, and only then we can apply hydrostatic pressure in all directions. So somehow over here between the two diamonds, we have to create a little vessel, if you like, into which we can add some fluid and then add a little piece of the crystal, and that fluid, when compressed or pushed on by the diamonds, will produce hydrostatic pressure. So in order to produce that little vessel or the sample chamber, if you like, we use a stainless steel gasket. It's a fairly thin sheet of stainless steel. It's pretty hard. But in order to make it harder still, we push the two diamonds against each other so that we make an indentation in that gasket. And now, that indentation, at the center of that indentation, we then drill a little hole so that we can now produce our sample chamber. So that little space in the center will be the place where we will end up putting our little piece of crystal. This is how it looks like in real life in our pressure cell. So in order to show you how things look inside that little chamber, I thought I'd show this to you from the top view rather than the side view that I've been showing you so far. So if you look at the diamond culet in the top view, we've got the diamond culet, and here is the gasket, the stainless steel gasket, and then there's a hole in the center that is the sample chamber. For dimensions, well, the culet is about 0.6 millimeters. The hole in the center is about 0.2 millimeters. So that's just a little bit more than the thickness of a human hair. Okay, so it's really kind of microscopic. That's why you see the stuff about not drinking coffee. And then inside that little hole, then, we put in a little piece of crystal. And we're kind of almost ready to go if we can put our hydrostatic fluid in. But then here's the other thing. How are we going to know how much pressure we have? We need to have some kind of a gauge in there, right, to measure our pressure. Obviously, there's no room for a physical gauge, but what is a standard use for high pressure physics is to use a little piece of ruby, because ruby has a very bright red line, a luminescent line, that one can track with the spectrometer, and it shifts in a very predictable manner the pressure, and so we end up having an optical pressure gauge sitting in the pressure cell along with the sample. Okay, so at this point then one puts the whole cell together and one gets the fluid put in. And I decided not to show you all the details of how we put the fluid in, but just take my word for it. One does put in the hydrostatic fluid, which turns out to be liquid argon in our case. And now we are ready to do the experiment. If we send in a beam of laser light, hits the sample, then one can see the whatever light that the sample emits. And then if one moves that laser beam over to the ruby, then we can look at the emission from the ruby and therefore calculate the pressure. So that's sort of how the whole pressure cell is put together in order to do the experiment. Okay, so now let's move on to the next phase, which is to learn about the experiment itself that we did, or at least one of the experiments that we did. And that experiment, the one I'm going to describe to you today, is one where we studied a semiconductor. Actually, we studied a semiconductor quantum well under pressure. So, semiconductors, and I'm sure many of you are familiar with this, but real quick, semiconductors are materials that conduct electricity with an efficiency that is much better than that of insulators and somewhat worse than that of metals. So its conductivity is intermediate to that between insulators and metals. And the reason for that is because semiconductors have what is called a moderate-sized band gap. Excuse me for just a second. All materials, all atoms, have a positive core of nuclei and other interior electrons. And outside this positive core of the atom are the outer electrons. So the outermost electrons in an atom are the ones that are called valence electrons, and they are the ones that determine the chemical properties of the material. In a metal, the outermost electron is bound to the positive core with just a very slight amount of energy. So just a little bit of energy will kick that electron out of that outermost shell to the next higher energy level, where it can wander around easily and conduct electricity. So that's for a metal. So in a metal, if you like, there is a very small energy gap between the valence levels and the conduction levels. So the electron can just jump across, go to its conduction energy levels very, very easily. In a semiconductor, it requires just a little bit more energy to get from the valence levels to the conduction levels. And that gap in the energies is what is called the energy band gap. So for a metal, the energy band gap is pretty close to zero, whereas for insulators, in contrast, that energy band gap is very, very large, and therefore the electrons can't get out of here and go into the conduction carrier very easily. So just in very hand-waving terms, that's sort of the difference, that's sort of what causes the great differences in electrical conductivity. How does one, now this energy band gap turns out to be a key feature that is necessary in all semiconductors and forms the basis of, for example, all of the diodes and transistors and FETs and so on that are produced that of course form the basis of our whole electronics industry. It also determines the color of the material. So if one wants to figure out what kind of color semiconducting material is going to emit, then we've got to probe that band gap in some fashion. And there are many ways to do it, but the way that we would do it is to send in a beam of light of a fairly high energy, enough energy that an electron in the conduction band, in the valence band, can absorb that energy and then go up into the conduction band. This amount of energy that it absorbs is equivalent to that of the incoming light. Now, the electron doesn't just sit around in that conduction band. In fact, it stays in that spot over there for a very short amount of time, of the order of picoseconds, and it very quickly migrates to the bottom edge of the band. Not only does it migrate, that little empty spot that we left behind also migrates to the edge of the band. And then fairly soon after, of the order of nanoseconds, that electron sees that empty spot in the valence band and decides it's going to go right back down into the valence band again. And it loses in the process an energy equivalent to that of the band gap, and that amount of energy is emitted as a photon. So basically what we've done in this method is that we have light of one color coming in, one energy coming in, and then by exciting the electron and making it come back down, we have made the crystal emit another photon of a color or of an energy equivalent to that of the band gap. So this is a good way, if you like, of studying what the band gap itself is. And we will use this methodology to study the quantum well systems that we will be talking about in just a little bit. Now, before we get to quantum well systems, I thought I'd show you a little bit about the kinds of energy semiconductors have, the band gaps they have. So silicon, for example, has a band gap that's in the near infrared. In nanometers, that's somewhere around 1100 and odd nanometers. In energies, it's about 1.1 electron volts. Gallium arsenide is out here around 900 nanometers, sort of just in the near infrared, 1.4 electron volt, and so on with a whole bunch of different semiconductors that span that visible range. In fact, this green color over here that you're seeing comes from some kind of some mixed semiconductor on here, which has a band gap equivalent to that green color. So in applications, what one wants to do is to be able to find semiconductors of many different colors or energies so that one can use them for different purposes. But nature is not that kind to us. Not every possible color that you could wish for is available in a semiconductor or even in a compound. And so therefore, there were reasons why one had to come up with, folks had to come up with different kinds of materials so that they could tune some of these energies and get whatever energy they wished to have. And therein came the construction of semiconductor quantum wells. And these have been around for some decades by now, but they have been used in many different combinations of different semiconductors. So let me take you to a little introduction of how semiconductor quantum wells are made, and then that will take us into our high-pressure experiment. So, semiconductor quantum wells are materials where you don't have just one semiconductor, but you have layers of two different kinds of semiconductor. They kind of look like this. So you start out, let's say, if one wants to make gallium arsenide, aluminum gallium arsenide quantum wells. What one does is one starts out with a basic crystal, usually gallium arsenide. And I'm sorry, some of those titles have gotten cut off down here at the bottom, but this back piece over here is just gallium arsenide. And then what is done is one puts down layers, alternate layers of gallium arsenide and aluminum gallium arsenide. Okay, alternating layers of gallium arsenide and aluminum gallium arsenide. And I don't know if you can tell from just the little bits that you see over here, but this first, the lighter color is the aluminum gallium arsenide, the darker color is the gallium arsenide. Okay, so what does this do for us? Well, once this kind of quantum well is made, now the band gap structure is going to look somewhat different. For the aluminum gallium arsenide, one will have a bigger band gap, it turns out. It turns out that's about 1.8 electron volts. For gallium arsenide, one has a somewhat smaller band gap of about 1.4 electron volts. So what one ends up with is a profile, if you like, of conduction band and valence band, which looks like little fences. Now, what's the quantum well part of it? Well, it turns out that now if the electrons are, the electrons that one is looking at, we want to go into the lower energy level, the lower kind of band gap, which would be the gallium arsenide part. If one puts electrons there or just looks at the electrons in the gallium arsenide, those electrons actually end up seeing the walls fairly easily, and therefore their energy is getting modified slightly from the fundamental band gap of the host material. So what one ends up with is slightly different energies than the original band gap, and therefore that allows a certain amount of tuning, if you like, of those energies. There are also other reasons why this is a great invention, because it also helps with the efficiencies of certain transitions. Okay, so here's then our quantum well system. And now, if one wants to develop devices using this material, one needs to know a lot of different parameters, because without knowing the exact parameters, one can't, if you like, design field effect transistors or light emitting diodes or whatever. So it turned out that for the gallium arsenide, aluminum gallium arsenide system, the quantities that were not known for several years was the depths of the wells. Okay, so let's just, I guess I had a little bit more for you on how the transition looked like. Okay, and the question of the that arose for these materials was, what were these well depths? So we have these. Everybody knew that the aluminum gallium arsenide has a band gap of 1.8 electron volts. Gallium arsenide is 1.4 electron volts, which means there's a difference of 0.4 electron volts. But what was not known for quite a while was how much of that 0.4 electron volt difference wound up in the conduction band and how much wound up in the valence band. In other words, was it 0.2 electron volts in the conduction and 0.2 electron volts in the valence band, which would be 50-50 kind of mix? Or was it just 10% of the difference in the valence band and 90% of the difference in the conduction band? It turned out that a lot of the room pressure measurements could not determine this answer. In other words, even though one can do fairly detailed studies of all these energy levels and make models of them and make calculations, it turned out those calculations were really very, they were not sensitive to how deep these wells were. And knowing the depth of the well was very important to designing devices. So this is where some of our high pressure measurements came in to answer that question. So by doing a high pressure measurement, we found that we could answer a question about parameters that were needed at atmospheric pressure. Okay, so in order to see how we did that, we need to look at one more conduction band. So far we have just looked at the topmost valence band and this bottom conduction band. But there are a whole bunch of higher energy levels as well. So let's look at one more conduction band on top of, above the first conduction band. And here was a scheme that would allow us to answer the question of how deep that quantum well was. If we could look at a transition from the X conduction band in aluminum gallium arsenide, remember the lighter ones are the aluminum gallium arsenide, since I've lost my captions there. If you look at a transition from the X band of aluminum gallium arsenide to its own valence band, and then look at a transition from the X band of aluminum gallium arsenide across to the valence band of the gallium arsenide, then all we have to do is to subtract one value from the other to get the depth of the valence band. Okay? So, very simple method of figuring out the depth of the valence band. Okay? So let's see what happens if we just take a piece of well material and shine light on it. You should be able to make this measurement, right? Okay. So here we are. We shine, say, here's an electron sitting in the valence band, shine in a beam of light, gets absorbed enough energy that it can take you above X. Because the whole idea here is to make that electron come down here and then make the transition. Alright, so let's see what happens when we do that. So here is our electrons going to go all the way up above X. And now, if we could only convince it to go where the green line starts, we're in good shape. But if we look at this transition, here's what the electron does. It just kind of knocks around, back and forth, here and there. It does not want to stop at this well at all. It always wants to come down to the lowest possible energy level that it can come down to, and only then will it make that transition and emit the light. Okay? So, it's a nice scheme, but it's not going to work as long as that X conduction band is above this bottom blue G conduction band. The only way to make this work would be if somehow, through some method, through some magical method, of course using high pressure, if we could move this G conduction band up above this X conduction band, make this X conduction band be the lowest conduction band, then we will be able to see this transition and therefore obtain the valence band, offset the depth of the valence band. Okay? And that's the experiment that we did under hydrostatic pressure. So what I'm going to show you in the next few slides is a series of the positions of these conduction bands as we apply pressure. It turns out that as one applies hydrostatic pressure, this G conduction band relative to the V goes up in energy. The X conduction band relative to the V comes down in energy. It's just the characteristic of those energy levels. In fact, the G goes up way faster than the X comes down. And at some point, they cross each other. And at the point at which they cross each other, the X conduction band will start being the lowest conduction band. This is what our basic spectrum looked like for this transition over here. And now let me take you through a whole series of band configurations and show you where the energies lay. You'll notice that at zero pressure, the energy lies somewhere around 1.52 electron volts, and that will be our starting point. So here we are. We start off with zero pressure over here, and there is our energy point. This is an energy versus pressure graph, and here is where our transition occurs. Apply a little bit of pressure, G goes up, X comes down a little bit, and there is our next point. This transition has come to a higher energy. Next pressure, higher still. Next pressure, higher still. You notice how the G and the X are getting closer and closer to each other. Higher still. And now we are almost at the point where these two energy bands, these two energy levels coincide. And at the very next pressure that we have, the G will have gone above the X, and we should start seeing a transition from the X conduction band. Here we are. Next pressure, and there we are. We continue to see the transition from the G conduction band, but we also start seeing a new transition from the X conduction band, as you can see in this graph over here. And as pressure is increased, we get more and more data points along our graph until we get to about 7 or so gigapascals, which is the edge of this particular graph. So very nice. We now know where the energy of that X transition is at 6.8 gigapascal. But we want to know what it is at zero, right? That's simple now. All we've got to do is to extrapolate this line backwards, and we now know then that that's where the energy of that X conduction band should have been at zero pressure. So that then tells us that the position for zero pressure is going to be at 1.92 electron volts, as it turns out. And now what we can do is go look up from other experiments what the energy of the X to B transition is in the aluminum gallium arsenide, 2.04 electron volts. Subtract the two values to give us a depth of 0.12 eV. And now that we know that the valence of band depth is 0.12 electron volts, we know that the rest of it is going to be 0.4 minus 0.12, which gives us a ratio for the depths to be 70 to 30%. Okay, so here then was an experiment where we were able to do an experiment at high pressure to figure out a property that then could be extrapolated backwards and to determine a value at zero pressure, which you could not actually figure out at zero pressure itself. Okay. So after this experiment, we did several different experiments that I'm not going to tell you about, but there's a whole variety of things that one can do with the quantum level structures. This work went on for several years with several different materials. Okay, so now, I think we're coming to the very end of the talk. And what I'd like to do in the next 3 or 4 minutes, since it's really not going to take much longer than that, is to talk a little bit about superconductors. Superconductors are materials where the resistance of the material drops precipitously at a particular temperature. Usually the temperature is very low. In a normal material, a normal metal if you like, the resistance of the material decreases as temperature is decreased, and then after a certain point it more or less flattens out. In a superconductor, there's also a decrease in this resistance, but then it doesn't flatten out, but just suddenly drops by 4 or 5 orders of magnitude. And this is what is called superconductivity. There are several other aspects also, of course, that are associated with superconductivity. But what I'd like to just point out today is the places where high pressure has made an impact on the study of superconductors. The first superconductor that was discovered was mercury in 1911. Campanions discovered that mercury was superconducting at about 4.1 Kelvin, very close to the temperature of liquid helium. He and a collaborator actually started doing pressure experiments also fairly soon after, because they realized that there were intermolecular or interatomic forces that could be played with by applying pressure, and then that affected the temperature of the transition of superconductivity. So the superconductivity transition temperature is sort of the key thing that one can play around with high pressure. There are about 51 elemental superconductors that have been discovered so far. About 25 of them are superconducting at normal pressures. Several of the others, the other 26, are actually superconducting at high pressures. One of these materials is actually silicon. See right over there, the periodic table. Silicon is a semiconductor, but when you apply enough pressure, it actually becomes even a superconductor. So the whole idea of finding new superconductors, as well as maybe synthesizing new kinds of superconductors, is something of interest to the high pressure community. Here, if you like, is our galaxy of superconducting materials. It only goes to 2010, so it doesn't include the newest discovery of last year. Until about 1986, most of the superconductors, or pretty much all of them, were superconducting only below about 30 Kelvin. Now, helium is liquid at about 4.2 Kelvin, and the next easy to find liquid element is liquid nitrogen, which is up here around 77 Kelvin. So the search was really for a material that would become superconducting at liquid nitrogen temperatures, because liquid nitrogen is just so much cheaper than liquid helium. That was the year in which, 1986 was the year in which a new family of superconductors was discovered, lanthanum and barium copper oxide. And you notice that in the very next year, this transition temperature went up almost by a factor of 2 to about 80 Kelvin. And that discovery involved high pressure work. The LBCO, the lanthanum and barium copper oxide materials, were discovered by Rednose and Miller, for which they got a Nobel Prize. And they have a crystal structure that looks sort of like that. Now, this material was superconducting at 27 Kelvin, not very exciting. But being that it's a completely new class of materials, it was of course of use to study these under pressure. And that was what was done by Paul Chu and his group in that same year. What they did was they took lanthanum and barium copper oxide and applied pressure to it, measured the superconducting transition temperature, and they found that it went up. Which basically meant that as you squeeze these copper oxide planes and chains closer to each other, the superconducting transition temperature increased. So Chu got the idea that if he could replace this lanthanum ion here, which is rather large, by a much smaller element, then maybe what that would do is kind of automatically squeeze the whole cage, bring these copper oxygen planes and chains closer to each other, and increase the transition temperature. And that is in fact what happened. By substituting yttrium for lanthanum, yttrium barium copper oxide, which is a very famous LBCO, was discovered with a transition temperature of 92 degrees Kelvin. Pressure has also played a role in all kinds of other materials. Until last year, the record was held by this naturally compound, which had a transition temperature of 133 Kelvin at atmospheric pressure, but 165 when you apply pressure to it. Last year, a new material was discovered, the well-known hydrogen sulfide. They don't think it is H2S, they think it might be H3 or some kind of mix of that, but that's all that it is, a very simple material. And this material is superconducting, as you will notice over here, at almost 185 Kelvin. So the race is on. Everybody would like to have a room temperature superconductor, and maybe we will find one day. This is our team. Thank you very much.
my privilege and honor to express my sincere thanks to Dr. Meera Chandrasekhar for giving such a wonderful talk on semiconductors and superconductors under high pressure. It has been very informative and interesting talk with us. On behalf of Bangalore Science Forum and all of us here, I propose vote of thanks to Dr. Meera Chandrasekhar. Tomorrow's talk by Dr. K. Radhakrishnan, former chairman, ISRO, will be speaking on space commerce recent trend. All are cordially invited. And question and answer.
Good evening, ma'am. Ma'am, I have two questions. The one is regarding depth well, the quantum well which you showed. What does it signify, the difference in the valence in the conduction band, the difference in the energy band? Because one was the 0.2 electron volt and the other was the more. Does it have special significance, or what is the reason for the difference in the energy level?
Okay, let me see if I can. Could you repeat the second part of your question? What is the difference between?
The valence band and the conduction band had a different energy level.
Discussions taking place. It won't go more than 10 minutes. Please wait.
What does it signify? Why is it like that? Why is it 50% and why is it 10 and the 90 and not some other percentage?
Okay, so a lot of that depends on the basic band structures of those materials itself. This is the value for that particular pair of compounds, gallium arsenide and aluminum gallium arsenide. When you put other kinds of materials together, one finds different kinds of band offsets. So the reason for that actually lies in fairly complex calculations of of bands themselves, which involve many-body calculations and so on. It's not kind of a real quick and obvious thing.
And the second one is there something like a negative resistance in the superconductors? We go up to zero resistance where it's called, there's no negligible resistance or no resistance at all. Can we go to a negative part of the resistance where we can say that the material is a negative in resistance?
Okay, so a negative resistance would imply that if you apply a voltage in one direction, the electron will travel in the other direction. So pretty much with superconductors, the ceiling, if you like, is pretty close to zero. So it's usually of the order of 10 to the negative fifth, sixth, and so on.
And why is it that only few materials exhibit a superconductivity and why others don't? Is it something to deal with the Cooper pair forming or with the other effects?
Exactly. A Cooper pair has to form in order for superconductivity to occur. So, and it's not always, in every material, there might not be the right kinds of interactions in order to form that Cooper pair. So that's sort of the reason why not everything is superconductive.
Thanks a lot, ma'am.
Madam, thank you very much. Your first, resting and what is that thing that Madam what test applications on it?
You're breaking up. Yeah, your voice is breaking up.
Super. Madam, latest applications I wanted. Superconductors and semiconductors at high pressure, especially apart from space, this one and what are the other fields?
Okay, so very often high pressure is actually used as a method to study some of the mechanisms or to look at how materials behave in that environment. So the applications really tend to be more for one of understanding what's happening in those materials. So for example, one of the major predictions in high pressure was that hydrogen would become metallic at very high pressures. And this has sort of been something like a holy grail that a lot of people have been chasing. Now, why would you care whether hydrogen becomes metallic? Well, it turns out that in very large planets, for example Jupiter, They don't really know, for example, the reason why all the magnetic fields of Jupiter are what they are. And the pressures inside Jupiter are extremely high. And so there's metallic hydrogen in there, and of course that changes the mechanisms of why, for instance, the magnetic fields are formed and so on. So a lot of it has to do with understanding various features of a fundamental kind of a process. In terms of applications, we find that, for example, in semiconductors, a lot of the one can actually try to look at how different materials might be synthesized. So the YBCO is one such example, where directly kind of told people what kind of new superconductor to make. And the same is true for certain other organic materials.
Thank you, madam. It was very interesting.
Good evening. Good evening, ma'am. First of all, thank you for a wonderful talk. I had 3 questions actually. Yeah, I'll start with the first question. The first question is when you're talking about very high pressure, the other factor that comes to break mind is the temperature issues. So what is the typical temperatures that we are talking when we are talking of such high pressure experiments is my first question.
Okay, so one can do high pressure. Remember, the volume of the whole thing is very small, and so one can pretty much hold it at whatever temperature one wants. In fact, all of our experiments were done either at liquid helium temperatures or liquid nitrogen temperatures, because it just makes the optical transitions easier to observe. But people have in fact done high pressure experiments even at elevated temperatures. So it depends on what they're trying to study.
So the temperature issue is not a major factor as such?
No, because you're holding the temperature at a certain value. You're attaching the low pressure cell to, let's say, the bottom of the cryostat. You're externally holding the temperature at wherever you want it.
The second question was with respect to these transitions happening between the higher quantum level wells and the lower quantum wells. How exactly do we know that the transition is happening from a higher well to a lower level well? Because there can be multiple levels of wells and the transition is quite unpredictable. Is there any theory that predicts this transition rates and transition probabilities?
Yes, there is. Now, first of all, let me give you kind of a couple of different aspects to this. When one does luminescence experiment like we were doing, then the electron, the highest transition probability is always from the bottommost, the levels that are closest to the edges of the bands. Okay? And that is very well predicted and very well known. If one wants to study the higher energy levels, then one has to do a different kind of experiment, as it turns out. One has to either do an absorption experiment, or one has to do some kind of coordinated reflectivity experiment, which in fact Chandrasekhar did several of those experiments with his students to study some of the higher levels as well. So it is possible to program that you have to choose the experiment that is best for your study.
The third question was with respect to the superconductors. The main reason for studying superconductors is their application in daily life scenarios and to improve the computational systems, so on and so forth. So what are the challenges in implementing high pressure superconductors in such scenarios where, for example, if I have to have a superconducting computer, for example, is it very, very feasible or liable to have a high pressure superconductor implemented to such systems?
I think it would be very difficult because first of all, the sizes involved are tiny, they're microscopic. So I think to expect a high pressure system to be used in a piece of equipment is probably unlikely. I suppose one should maybe make a lighter looking battery and found something very fancy, very special to do, but it would really not be very practical. So it really turns out to be a tool that you can use to design other materials.
Thanks a lot.
Thank you for awesome lecture. And I have this one question about semiconductors and devices. And these semiconductors and diodes work on quantum tunneling. And I wanted to know about how these devices work, and is there any way to increase the efficiency for better quantum computers?
Okay, so this is a pretty detailed kind of a question. I don't know if I have a quick answer for you. It involves many different kinds of parameters. Yeah, it's probably a chapter somewhere in a physics textbook.
You want to ask questions? Yes.
Mentioned regarding diamond angle pressure, which produces pressure. I just want to know if there's any substitute for diamond substance. Instead of using that, is there any other substance which produces pressure?
Okay, other materials have been used. Sapphire has been used, but really diamond has sort of been the workhorse for all these years. In fact, it's just such a good material that there has not been a good substitute. It's hard, that's one thing. The second thing is it's transparent. Okay, so that's the second thing that really helps. Now people do use synthetic diamond as well.
Good evening, madam. Thanks a lot for the very first session you have today for us. I just wanted to know one thing. As I heard, the latest material in semiconducting research is indium antimony, and which holds a temperature up to 571 C. Is there any details about that? And they have been, I heard that they have been used in many of the magnetic sensors in this space applications. And do you have any details on that?
I didn't get what you said about what the material was. You kind of broke
it was INSP, that is indium antimonite.
Indium antimonite? Well, indium antimonite, so this is in what kind of application were you thinking about? In diodes, is it?
In the field of semiconductor.
Right. It's been used for various kinds of devices. It's sort of our infrared material. I don't know what the latest is on it, but just sure it's a material that's been used fairly frequently.
Thanks.
Excuse me, that will be the last question. Afterwards, we will be here. We will be going towards the gate and other things. You can be with us and discuss. This is the last question.
Superconductor technology of 1911 onwards coming. Semiconductor started with the germanium later, but a transition of graphene now impact to in that one breakthrough is a carbon material or gallium arsenide going to be a cost effective. Now that impulse is completing the world traveling with the solar energy. Like that, any superconductive material will reduce the cost in computing and energy sector.
Well, I think that has sort of been one of the reasons why people have been trying to use many of these materials, is to see if one can easily cool the materials down. I couldn't tell you the latest for it. I don't know what the latest material is. The graphene materials and the organic-based materials are the ones that are sort of the up-and-coming ones as far as applications for solar cells and transistors and so on are concerned. And I don't know whether they're going to be able to marry the whole superconductivity part along with the semiconductors, but that would certainly be great.
I think by thanking Dr. Meera immensely, I brought this lecture.